Hello everyone, thanks for being here. But due to some technical issues, my co-author, Zhiyu, who intend to co-present this work to me, but cannot present. But I still want to introduce this excellent collaborator, Zhiyu, and he did a great job to this work. And I'm Wei, and here today I'll walk you through the JITServe, an SLO-aware LLM serving system that handles imprecise request informations. And this is a joint work with our collaborators at UIC, Cisco, and Google researchers. So let's get started. Let me start with some context. LLM today power a remarkably diverse set of real-world applications, like from interactive chatbots like Gemini or ChatGPTs to coding assistant like Cloud Code or in Cursor, and to productivity duties and even entertainment. So what's important here is that all of these workloads are now served by the same underlying LLM infrastructures, even though they differ dramatically in how users actually consume these responses and service. And leads to our first observations. The SLO requirements are highly heterogeneous. To ground this, we conducted a user study covering over 500 participants across 6 academic and industry organizations. And the table on the bottom summarizes how users actually consume LLM response across 6 application classes. And you will notice that no single category dominates. So the takeaway is the user will have diverse SLO needs, both across and within the applications. So no single latency metric like TTFT and TBTs can capture them all. To make this more concrete, let's categorize the LLM serving request. The first type is latency-sensitive request. And thinking about the users are reading a chatbot response, and each token must arrive in time to match the user's reading pace because the user will expecting a streaming and smooth response in interactions. You can see this on this slide. The tokens with green bars are generated fast enough and meet their SLO, while tokens with red bars like in time to 3 words here fall behind and miss the SLO. So both TTFT and TBT matters in this request on a per token basis. The second type is deadline sensitive. Here, the full response feeds into the downstream tool that has a hard timeout. Intermediate tokens timing doesn't matter. What matters here is whether the response arrives before the deadlines. So the relevant metric is time to last tokens, or TTLT. The third and most challenging type is the compound or agentic request. In the agentic workflows, a single user request will usually expand into a DAG or LLM calls and two invocations. So look at the diagram on the slides. The orange path highlights the critical path through the DAG, which is what ultimately determines the end-to-end latencies. The other branches run in parallel and don't dominate the timing. So for compound request, what the user actually experiences is the end-to-end latency along this critical path. Putting all 3 types together, a latency-sensitive request cares about TTFT and TBT, and deadline-sensitive request cares about the time-to-last tokens, while the compound request cares about the end-to-end latencies. The key challenge here is a single serving system must satisfy all 3 at once. Given this, we define the SLO and goodput uniformly across all 3 request types. For latency-sensitive requests, the ICE tokens only counts if it delivers before the TTFT plus I times TBT. And for deadline-sensitive request, all tokens count only if the full response finished before its deadlines. For compound request, all tokens count if the entire DAG finished on time. So the unifying rule is simple. A token contributes to a goodput only when its SLO is met. So this gives us a clean optimization target. Now, the harder question is, how do we actually schedule this request? The challenge is that we face 2 kinds of uncertainties. The first is structural uncertainties. For agentic workloads, we don't know the execution DAG or even the number of LLM calls during the runtime. The top right CDF shows that how widely calls counts can vary across mass reasonings, multi-agent, and deep research applications. The second is length uncertainties. And as the bottom right figure shows, even the state-of-the-art LLM-based predictors are highly undesirable, with prediction errors that span a wide range. So we need new ways to capture both of this. Before introducing our solutions, let me share what motivated it. We found a striking misalignment between latency optimization and actual service goodput. Look at the rightmost bar chart. Today's latency-optimized schedulers like chunk prefill will miss the SLOs on a 78 to 91% of requests. And here's the surprising part. Even when we give the Oracle precise length information to the scheduling system, the miss rate is still over 50%. The lesson is clear. Lower TTFT or TBT doesn't not translate to lower SLO violations. And policy matters more than predictions. This is what motivates our just-in-time scheduling approach. Instead of optimizing latency aggressively, we allocate just enough bandwidth to meet each request SLO and refine the allocation online. This brings us to the JITServe. Our system has 3 core components. First, the request analyzer refines length and dependencies estimates online. And second is the SLO-aware schedulers, saying the Gmax algorithm, allocating the minimum bandwidth per scheduling time frame to satisfy the SLOs. And third, the SLO trackers monitors actual generation speed and feeds back to the correct estimates. The guiding philosophy is clear. Scheduling conservatively at first and relax estimations refine online. In the next 2 slides, I will dive into how we tackle the length and dependency uncertainty. For length uncertainties, we use quantile regression forest, or QRF for short, with 2 design choices. First, it's request adaptive. The quantile interval is customized per request rather than using a number of fixed buckets for everything. And second, QRF supports online refinement. As more tokens are generated, we feed them back to continuously sharpen the predictions. So accuracy improves over time instead of staying frozen at the initial guess. The top right fig plots shows QRF's arrow converge with the SLO bound, while Llama model predictors keeps drifting and violates the SLO. The bottom figures show that QRF is much faster at higher RPS, so it is lightweight, accurate, and refines online. For dependency uncertainty, especially for agentic requests, we introduce a pattern analyzer. The core idea is to represent execution histories at pattern graphs where LLM nodes annotate with input and output lengths, while 2 nodes will annotate with their execution durations, and match the incoming request to the closest historical patterns through similarity matchings. And to even keep this more efficient, we use K-metals clusterings to compress patterns, and we will also evict the low-use ones. The request execute and more tokens stages appears. We continuously refine these matchings, so our DAC estimate also sharpens over time. Together with our QRF, this gives JITServe a complete view of request uncertainty. So now the question is, even with the request analyzer providing estimations, the scheduler still faces 2 distinct challenges. The first is that the scheduling decisions must be made with imprecise and time-evolving information. The static decisions made at the request arrivals are simply too early, since the optimal decisions depend on the information that only becomes available later. In fact, we firmly prove that maximizing goodput even under complete information is already an NP-hard question. To tackle this, rather than making one-shot static decisions, Gmax decomposed the execution into different time frames, and within each frame, we will re-estimate every request minimum bandwidth to meet their SLOs and reprioritize accordingly. Second, our experiment shows that batches with mixed input lengths deliver significant higher TBT than homogeneous batches, even with the state-of-the-art kernel designs like flash decodings. So the scheduler must simultaneously optimize for goodput and batching efficiencies. While these 2 objectives are not always aligned, so forming a 2-dimensional scheduling challenges. Gmax addresses both challenges with a 2-step algorithm. First, for each request, we define its scheduling priority as the estimated goodput divided by the estimated generation time bandwidth, which capture the marginal goodput per unit. Intuitively, this naturally favors requests that deliver high SLO values at low bandwidth cost. Next, we sort the candidates by the input length and slide a window of batch size across them, selecting the group with the highest aggregated priority. Though within each time frame, we maximize the total SLO satisfying tokens that the system can deliver. This joint strategy ensures that we can keep input lengths homogeneous, which directly translates to faster per-step execution and better overall goodput. Finally, after each time frame, Gmax feed requests back to the request analyzer to refine length and dependency estimate. So based on these new estimations, we will compute their priorities and reschedule accordingly. To future prevent frequent preemption overhead, we only trigger the preemption when the projected goodput gain from admitting a high priority request exceeds the cost of KV cache eviction and swapping. We also provide a provable competitive ratio guarantee against the offline optimal schedules, where the scheduler has the full request information. So let's come to the evaluation setup. We evaluate JITServe on a cluster of 16 NVIDIA 800 GPUs across 4 models of different parameter sizes, both dense and MOE architectures. And the workload spans across both single and agentic request workflows, include requests from Alpaca and LM6 chat datasets and real-world applications like deep research and math reasoning. Our baseline includes standard baselines like VLM and chunk refill, and also policy baselines like least attained serving schedulings or learning to rank, which is a shortage job first variant. So the results are compelling. In our long-term online deployment experiment, JITServe actually maintains a consistently high and stable goodput. In contrast, baseline exhibit progressive performance degradations. That's because the baselines will have long requests accumulate in the queue, and these head-of-line blockings will lead to a growing SLO violation rate, and the gap widens over time. Under increasing load, all baselines show sharp goodput degradations, while JITServe's performance advantage actually widens as RPS increases, which demonstrate the particular strengths in congested and high contention scenarios. And crucially, we benchmark JITServe against an Oracle variant, noted at JITServe star in the top right figure, that operate with perfect knowledge of all response lengths and execution graphs. And JITServe actually achieves performance within 3 to 9% of the oracles, despite relying on the imprecise and online refinement estimations. So this near oracle result validates that our uncertainty estimations and scheduling strategies together effectively compensate for the missing informations. So to wrap up, the core insight behind JITServe is that even without precise request informations, you can still make good scheduling decisions. The key is to start conservatively by allocating just enough bandwidth based on the upper bound estimations, and then continuously refines as generation unfolds, which will release the excess capacities to maximize goodput. Put together, JITServe succeeds in handling the full diversity of modern LLM workloads, from single chat to multi-stage agentic workflows, even with their own SLO requirements, while achieving up to 80% resource savings. So that's the conclusions of our presentations. Thanks for listening.